All right, so today we're going to start with section 5.1. We're taking a look today at the natural logarithmic function. Specifically, we're going to be looking at differentiation. I don't know that we're going to get finished today. We will see, and we'll see what that does with all the homework and things moving forward, okay? All right, so to start with, I would like for you to remember a few details that you know from last semester specifically. So if we have the antiderivative of x to the n, then that is equal to x to the n plus 1 over n plus 1. I know you all remember that, right? Power rule is one of the most common ones for us to remember. We always put the plus c on the end. But there's one thing that you might not remember. This power rule only applies when the n value is not equal to 1. Negative 1. The n value is not equal to negative 1. So what happens when the n value is equal to negative 1? All right, so if you have the antiderivative of x to the negative 1, that's the same as having 1 over x. We are going to define a logarithm to be the antiderivative of that. You've seen logarithms before, but probably nobody has defined them that way because you didn't have antiderivatives by which to make that definition. So the definition of a natural log is that it is the antiderivative of 1 over x, by definition. Now, this only works for x values that are larger than 0. We'll talk about that a little bit more in a moment when we talk about the graph of natural log. So the domain is a set of all positive real numbers. That's why that's the equivalent of saying x is greater than 0. And I want you to be familiar with this notation, just in case you see it somewhere. This is notation in some books. R is the real numbers. Sometimes it's bold. It doesn't look like these double lines. Sometimes it is drawn and it looks like double lines. When I write it down, I usually write it like this, so the double line's just on the left. It's all the same stuff. It means real numbers. And then we put a little plus sign after it to mean the positive real numbers. Okay? Bigger than 0. Okay, so we're going to start with what we remember. A lot of what you're going to see today is going to feel like I already know this, or maybe you don't know it right now, but you'll like, I feel like I learned this before, and you did. This is algebra. Probably saw it in an Algebra 2 course, or maybe Algebra 3, math analysis, pre-calculus, some variation of those things, college algebra, logarithms. So, and then we'll go a step further into the differentiation part. Okay, so the graph of a logarithm looks approximately like this. And it's crossing here at the number, or the x value of 1. So this is the rough graph for a logarithm. Notice I didn't put any scale on there because that's sort of not the features part I'm looking at, except for that x-intercept. And then we're going to talk through, and you can write down the different features of this graph. Now, the first feature is the one I marked. The x-intercept is at 1, 0. There is no y-intercept. Right? It doesn't cross the y-axis. And in particular, it's not crossing the y-axis because there's actually a vertical asymptote at the y-axis. And the equation for the y-axis is x equals 0. So there's a vertical asymptote at the line x equals 0. It increases without bound. So what does that mean? Well, it means that it's always going to be increasing. Now, it doesn't increase fast. My picture sort of alludes to something that's not quite true. It looks like it's sort of shooting up kind of quickly, and it doesn't really do it quickly. It does it slowly, but it does continue to increase indefinitely. In other words, there's no horizontal cap to this thing. There's no place beyond which it won't continue to go upward. The notation that we have seen back in chapter 2 about limits is that the limit of the chapter 1, the limit of the natural log of x is equal to infinity as x approaches infinity. Right? That's what it means to increase without bound, is that as we move in this direction, it continues to increase. So as x increases, y increases. I already talked about the domain. I mentioned that on the previous slide. The domain is all x values that are positive, or 0 to infinity. So we get the right-hand side of the graph. The range is everything, though. It can go down to negative infinity on y-axis, go up to positive infinity on the y-axis. It's going to do it slowly, but it would get there eventually. Continuous, right? You can draw this with one movement of your pencil. There's no holes, there's no jumps. There's nothing like that. It's actually smooth as well. I don't have that listed, but it's smooth, right? There's no jagged parts to it. We saw some places like where derivatives didn't exist, where they're like sharp turns. We don't have any sharp turns in it, nothing like that. 8, you might not remember. 8 is called 1-to-1. 1-to-1 means that if you were to look at the horizontal line test, it would pass the horizontal line test. So more concretely, it means every x value is assigned to uniquely one y value. That's what it means to be a function. But every y value has only one x value as well. That is unique to this graph in the sense that not all graphs have that. If you think about the graph of like just a parabola, like x squared, every y value that's present, with the exception of 1, has two x values that are assigned to it, right? So if y is equal to 4, then x could be 2 or negative 2, because 2 squared is 4 and negative 2 squared is 4. This doesn't have that. Every y value has a unique x value assigned to it, so it's 1-to-1. And then it's concave down. We talked about concavity last semester as well. Concave down has to do with the shape and how it's opening. It is opening downward, or it doesn't hold water, it dumps water, kind of a description. Does that all look familiar-ish from an algebra standpoint? This isn't calculus, right? This is all algebra stuff, and most of it you've seen, maybe not detailed quite like this, but you've seen these pieces before. Okay, so continuing in some of our algebra review of these things, we're going to sketch a graph, and it is a sketch. It doesn't have to have super specific things with it, but it will have some things noted. And we're going to use algebra techniques of transformations to do it. Okay, so this is not something that we've talked about together before, but you have seen it before. So there's two things in this graph that make it different than the previous one. Can you identify one of them?
It's going to be over at negative 2.
Okay, the plus 2 on the inside makes it different. It's going to move it somehow, right? What else?
It's negative, so it's
The negative. So there's a reflection going on. Okay, so we've got a shift going on and we've got a reflection going on. Let's talk about the shift, since that's the first one that Jackson mentioned, and it is the right one to start with because it's embedded inside. We always work from the inside out, kind of like when you're doing order of operations, right? We work from the inside outward. Okay, so there is a plus 2, and it's actually embedded inside with x. Okay, so anything embedded inside, do you remember how it shifts things? Braden's telling me. It's horizontal shift, so it's going to move either left or right. Do you remember which one this is? It is left. Anything that happens inside is sort of intuitively opposite. So a plus 2 moves it left 2, a minus 2 would have moved it right 2. So the first thing I'm going to do is actually shift my asymptote. So I had an asymptote before at the y-axis. So the y-axis shifted 2 units left, would be something like over here. What would the equation of that be? It's x equals negative 2. So I've got an asymptote that's shifted over. I will identify that piece, right? The sketch will include that. The graph itself will actually move over as well. So what used to have an x-intercept at positive 1 will now have an x-intercept at negative 1. So I will have an x-intercept right here. We'll do that one. Okay, so there's my x-intercept. All right, what will the negative do? It's a reflection. How is it a reflection? Is it a reflection up and down? Or is it a reflection right and left? Do you remember? It is a reflection up and down. Okay, so anything that happens inside embedded with x affects the horizontal. Flipping it would flip it left and right. So if I had a negative inside of the parentheses next to the x, that would be a reflection, and it would move it over to the left-hand side of the graph as a reflection. Because the negative is on the outside, and it would have actually moved that x-intercept as well. I already marked my x-intercept in the right location, but if the negative had been inside, the x-intercept would have been on the other side of the axis. Okay, so the negative here is on the outside, so it's a reflection in the y-axis, so it changes y values. It flips them up and down. So instead of the graph increasing without bound, it's going to decrease without bound. And so the graph will look something like this. That's terrible. Let's try again. Ish. right? A little bit of hand waving. Besides the graph, there's one more thing the directions ask us to do. What do they ask for? State the domain. What is the domain for this? Negative 2 to infinity. And if you'll remember, we use a parenthesis to indicate that it can't actually equal the negative 2. And then we always use parentheses when we have an infinity involved. Okay, all that good so far? So there's going to be a little bit of graphing inside of WebAssign. Okay, the graphing in WebAssign is not my favorite, but you can manage it, I imagine. Okay, logarithmic properties are going to be super helpful later, which is why we're talking about them now. The graphing properties are like, we want to remember them, but they're not really super hinging upon everything else. This matters, these properties. And there's some other properties. These are the ones that are most important, so the ones I'm going to focus on. The natural log of 1 is 0. That's the x-intercept stuff, right? If x is 1, y is 0, so that makes sense from a graphical standpoint. The natural log of e is equal to 1. I'll come back to that one in a minute. When I have the natural log of a product, I can separate this, and it doesn't become the product of natural logs. It becomes the sum of natural logs. And that's a really good thing. And you'll see why. And an analogous statement is that if I have the quotient inside of a log, again, it doesn't become a quotient of logs. It becomes the difference of two logs. And again, that's going to be a really helpful thing for us. As is this last one. The last one says that if I have the log of some value to a power, that's actually a constant multiplier in front of the log. And this is really just a specific application of number 3. Imagine if this said natural log of a times a. I could separate it. It would become the natural log of a plus the natural log of a. And when you add two things that are the same together, that's the same as multiplying by 2. Okay, so it's actually just a very specific application, but because of the way we use it, we kind of write it as a separate statement. Okay, so the first thing that we're going to do is we're going to work with these properties. Again, this is like we teach it in college algebra here at OBU, working both forward and backward, either expanding, which is going to be mostly what we're going to want to do later on, and also condensing them back down, which is sometimes helpful as well. So here's our first one. We're going to use the properties of logarithms to expand the following, which is the natural log of 3 times e squared. Oh, I mentioned I was going to do something and I didn't do it. Let me come back over here real quick. I want to remind you of something. We haven't actually talked about these. We will get to them later in this chapter. But the natural log of, and we'll just use e because e is our variable we're using, or not variable, value we're using here, is the same thing as log base e. Do you guys remember that? That's what the natural log means, log base e, of, in this case, the e. So the little e, the e that's inside did not come down as a subscript. That's not what happened. It's still inside of this. And then anytime you have the log base, which is now e, of that same value, e, this is equal to 1. So later on, we're going to see things like log base 2 of 2, and it's also going to equal 1. Okay, anytime the base matches what the interior is, they're equal to 1. So just a reminder of that because it will come back up. Not today, but it will come back up. Okay, this one, natural log of 3e squared. So tell me something you see happening inside of this log. Some operation, some feature.
Exponent.
There's an exponent. What else do you see? Multiplication. There's a product. Okay, so there's a product and there's an exponent. Now, the exponent is on a single piece. It's not on the whole thing. So I'm going to work with the fact that there's a product first. So the first thing that we're going to do is we're going to separate this with the third property. I think it was third. Yep, the third property. And this is going to be the natural log of 3 plus the natural log of e squared. That's the product property separating. And then you noticed that we had the exponent. So now the exponent 2 is on everything that's inside of the log. So we can move it to the front. It's tempting to think you're done, but you're actually not. There's one more thing that can be done with this particular one. What is it?
Natural.
Yeah, the natural log of e is 1. That's the property we just looked back at, number 2 property. So the natural log of 3 plus this piece right here is equal to 1. So this is the natural log of 3 plus 2. It's perfectly fine to write it that way. If in looking at this, you're sort of tempted to try to add the 3 and the 2 together, you can't. The 3 is embedded inside of a log. It's like having a square root of 3. You know, like you can't just add a square root of 3 and a 2 together, right? Like they're not like terms. So if it bothers you to have it written this way, or you're concerned that you might think that you would want to add them together, you're also welcome to move the 2 in front. Just use the commutative property and write it like that. That would be acceptable too. So either of those are perfectly acceptable ways to write them. Sometimes your calculator, or if you're using an online calculator or WebAssign, might force a parenthesis in here. If it forces a parenthesis, you want the parenthesis just around the 3 only, right? So like my calculator forces the parenthesis. Every time I hit natural log, it forces a parenthesis, which means I'm going to have to close the parenthesis. So just be aware of that if you're using a device that does that. Okay, we're going to do the opposite now. So this was taking something that was a single logarithm and expanding it, right? Now we're going to take something that's expanded and we're going to condense it back into a single logarithm. So we have 3 separate logs here. At the end, we will have just 1 though. These logs are added and subtracted together, which means in a very real sense, we're using properties 3 and 4 sort of in reverse. We're starting on the right and we're moving to something that looks like it's going to be on the left. Okay? Now, the easiest way I think to think about that is that if the log is positive, then its interior is the numerator. And if the log is negative, its interior is the denominator. Okay? So what we see here is that this one's negative and this one's negative, which means both of those pieces, the interior of the logs, are going to end up in the denominator when we're done. Okay? It's sort of tempting to say, well, can't I just, put the first one in a numerator with the second one in the denominator or something like that? It doesn't work that way, because if you were to move the negative out in front, like undistribute or factor it out, right, you would actually have them being multiplied. So they do end up being multiplied together. Now, there's also a 2 in front. Okay? You could distribute the 2 to everything first if you wished. There's nothing wrong with that. Or you could wait till the end and deal with the 2, which I think is probably a little bit quicker of an approach, a little bit fewer steps involved. So I'm going to wait for my 2. Are you good with that? Okay. So the first thing we're going to do, leaving the 2 out in front, is we're going to rewrite this as a single log. So there's going to be natural log. If the value in front is a positive, which it is for x, it goes in the numerator. If it's negative, it goes in the denominator. So the x plus 1 will go in the denominator, as will the x minus 1. And again, if you were if your calculator forces a parenthesis after the log, you may actually have another set of parentheses sort of in here going on. Like it might actually require that. So just be aware. You don't necessarily have to write that, but be aware if you're using a device that requires it. Okay, what's going to happen with the 2 in front now? It's going to become an exponent. That's property number 5. Okay, so the 2 in front becomes the exponent of the log. So that means I have the natural log of everything that's here, x over x plus 1 times x minus 1. Whoops, there we go. And all of this is raised to a power of 2. Okay, not the log. The log is not raised to a power of 2. The interior of the log is. All that piece is there. So you can leave it written like this. That's perfectly acceptable. You also could have it written where you distribute the 2. So you have x squared, x plus 1 squared, and x minus 1 squared. That would be okay. There's no good reason to distribute and multiply out the x plus 1 to x minus 1. If you did, it's not wrong. There's just no reason to do it. You with me? Don't do more work than is helpful. It's just not helpful. So leaving it in factored form is usually preferable to foiling it out. Okay. Yes, Tanner?
Is there a reason we need to know what the notation would be if we wanted the square to apply to the natural log? Is that a thing that would happen?
You mean like if the entire log were squared? It would just have parentheses with the squared. So you'd have the log inside of there, and then you'd have a squared on the outside.
Not like true.
Right. And we will see something happen, but I don't think it's today when we're doing like derivatives, antiderivatives. more for the purpose of assessing whether or not you're paying attention to what is actually being squared kind of thing. So you might see that happen when we get to derivatives.
Okay.
Yeah. Okay, everybody good? Okay, we're going to make application of these rules in a slightly different way. It's not as crucial to what we're moving forward and doing later on, but it's still an application that I'd like for you to take a look at. So in this problem, we're actually given the approximate value of a couple logs. The natural log of 2 is approximately equal to 0.6931, and then the natural log of 3 is approximately equal to 1.0986. Okay, we're given those pieces of information. So while I understand that in your calculator you can simply put in natural log 2 over 3 and it's going to spit out a version of this, right? It's going to give you an answer. That's not the point of these problems. The point is to make use of the fact that they gave you the natural log of 2 and the natural log of 3 with the properties that are being used. For example, 2/3 is a quotient, right? You see division. So since we see division there, we can rewrite it how? With subtraction. So I can take this and I can rewrite this as the natural log of 2 minus the natural log of 3. Agreed? Okay. So, and then after that, I know the value for the natural log of 2 and the natural log of 3. The natural log of 2 they gave me was 0.6931, and natural log of 3 is 1.0986. And then I can actually subtract them. Okay, so what do you get? Does anybody have their calculators with them today? I hope so. 1. Good job, Tanner. Glad you have a calculator. He's going to subtract for us today.
Negative 0.4055.
Excellent. Everybody good with that? Okay, so, and this one being what it is, and assuming that they didn't lie to you and tell you a wrong approximation for the natural log of 2 or the natural log of 3, you could actually check with your calculator and type in natural log of 2 over 3 and check that it actually works. A variation of this that wouldn't be able to be checked is what if they told you the natural log of x is equal to this value and the natural log of y is equal to this value. What now is the natural log of x over y? Right? Then you'd have to use the properties. You wouldn't have another choice. Okay, B. B is not as obvious about what to do as A was. In A, I saw a 2, I saw a 3, I see division, I can use it as subtraction. I don't see those things at the get-go with the number 81, but they're able to be used. Any idea how? Yep, so you can split up into sum of logs or into multiplication, either way. Okay, so 81 does break down. Let's just pause for a moment and do that. 81 is equal to what? 9 times 9, and then the 9s are going to be the 3s. So how many 3s does this give us? 4 of them. So you can either rewrite this as the natural log of 3 times 3 times 3 times 3, however many 4 of them are. I don't know if I said 4 of them at this point, but natural log of 4 3s. Or maybe in a little bit more of a condensed form, you can rewrite this as the natural log of 3 to the 4th. Okay? Then what? Yeah, we can multiply with the 4, right? The 4 will be a constant multiplier in front. 4 natural log of 3. And we were told what the natural log of 3 was. It's 1.0986. And if we multiply that out, this might be the last one that we need for Tanner.
It's 4.3944.
Ah, thank you, Pierce. 4.3944.
Yeah.
Excellent. Okay, all good? All right. So everything we've done so far, maybe with a little bit of an exception of some notation about limits, is pre-calculus, right? It's all stuff from algebra somewhere along the way. So the next part isn't, because it's actually talking about limits. Limits is what we did at the very beginning of Calc 1 last semester. in section 1.2, I think it was. And we started looking about what happens with limits as they approach certain constant values, like numerical values. And then later on, we looked at what happens as x approaches like these infinities and negative infinities, okay? So we're going to consider that graph of y equals, hang on, make this solid, the natural log of x, and I'm going to draw a small version of it in here so we can reference it. Looks something like this. And we're going to consider the following limits. Now, the first one we've already considered. As x approaches infinity, what does y do? It goes up, right? Indefinitely. We already wrote this property down. As x approaches infinity, y approaches infinity. That's the right-hand corner of our graph. Now, when we look at these next three, they're all approaching 0 in different ways, right? The first one says x approaches 0. But if you remember, what that means is it has to approach 0 from the right and from the left. And that's what the third and fourth one are. 0 plus means from the right, from the positive side of the graph. And 0 minus means from the left or the negative side of the graph. So I want to do those two pieces first and then go back up to the one that's just going to 0. All right? So we're going a little bit out of order. So x approaches 0 from the right. Well, if x is approaching 0 from the right, it means that it's going downward like that. Because x is getting close to the y-axis, that's x equals 0. So what is the value for y that we're approaching? It's negative infinity. So this one right here is negative infinity. What about x approaching 0 from the left? Nope. It doesn't exist. Why? It doesn't go towards anything, does it? The domain doesn't include those values. Values on the left-hand side of 0 are not in my domain. So it doesn't make sense to even talk about what's happening there. This does not exist because the graph does not exist on that side of my axes. So remember, when I'm looking at two-sided limits, which is the one that I've got left on the screen, x approaches 0, I have to consider both sides. If both sides approach the same thing, we're good to go, and that's the limit. If they don't, then the limit does not exist. So this one that we skipped up here is it does not exist because there is no left-hand limit to be discussed. Does that make sense? Okay, I'm going to flip back a couple screens before I move forward. Right here, we defined the integral of 1 over x to be the natural log of x. That is what the natural log of x is by definition, right? That was our definition. We didn't have a way to define it, so we created something new that defined it. That's what it really is. So when we get to our next slide and we're asking ourselves what in the world is, whoops, did I skip one? Oh, I did. I'll come back to that in a second, since I've already started talking about this. When I'm talking about what is the derivative of the natural log, the derivative of the natural log has to be the thing that we defined it to be the antiderivative of, right? The derivative of the natural log is 1 over x, as long as x is greater than 0. So what you'll see happen a lot of times, instead of this being written this way, is that the, I didn't say it that way. Never mind. It is x is greater than 0 because that's the definition for x. That's fine. I'll leave it like that. I was about to move somewhere else, but we're not there yet. It's next section. Okay, so we're going to get to derivatives. Sorry, I skipped one. Let me go back and get that one. Right over here. This one wants us to find the limit of a different graph that we haven't done yet before. Our graph is the limit as x approaches 6 from the right of the natural log of x minus 6. So a graphical perspective is helpful. You can do numerical. We could look at a numerical perspective and look at tables. That would be okay. You could do that in your calculator if you'd like. But a graphical perspective, based on what we've done so far today, is also another approach. What is the x minus 6 going to do inside? Shifts it to the right 6. So my x equals 0 asymptote is now going to be at, over here, shifted over to x equals 6, right? I crossed originally my x-axis at 1. And if I shift that x equal 1 over, I'm now crossing at 7. And the graph has this basic form. So this is the basic graph that we're talking about here. So having a perspective of the graph, whether you actually draw it out or whether you just think about it or even whether you use your calculator to draw it, is a good perspective. If I want to find the limit as x approaches 6 from the right, what would that be for this graph? It would be negative infinity. Okay? Just like the x approaches 0 from the right on the original natural log graph was. Natural log of x graph was. Okay, are we good? I was just so excited to get to derivatives. I was done with limits. We're going to do derivatives now. You ready? Okay. All right, so our derivative of the natural log of x is 1 over x. You good with that? This is a new derivative rule. So if you think about like your list of all your derivative rules that we've created before, like last semester, this is like number whatever on the list. It's the next one that comes. There's going to be a few more that we're going to add in here before we get to your gateway, but this is the first one. So we're going to actually find some derivatives. Okay, so yes, limits are calculus, but like derivatives are like really the calculus that you think of when you think of calculus, right? So we're going to do this calculus today. Now, as we work through this, keep in mind all the other things that you have experienced last semester, sum and difference rules, products and quotients, chain rules. All those things are going to exist. We just have an additional log rule now to use with them, okay? So on the first one, we have f of x is the natural log of x minus 1, okay? If the derivative of the natural log of x is 1 over x, what would the derivative of the natural log of x minus 1 be? Yes, 1 over x minus 1. And technically, the x minus 1 is inside of log, which means there's a chain rule here. It's just not a very exciting chain rule because we want the derivative of the outside, which we did. That's the 1 over part. But what's the derivative of x minus 1? 1. It's not very exciting, right? It's pretty boring. So we don't usually end up writing it because it is just a 1. If you want to remind yourself of that, feel free to write times 1 right at this point. And there's no simplification because multiplying by 1 doesn't change anything. So this is our first derivative that we've taken with this new property, this new rule. Now, b. B is more exciting because it's got more going on the inside, right? What do you notice going on the inside for b? A quotient. Do you also see that there's a power on the x squared, which means that there's a chain inside of the quotient, right? It's not just a derivative of one of the denominator. So you've got some chain going on. This is kind of messy. You could do it. I mean, you could do it. We could take a quotient rule with the chain rule here. Like we could do all of that, but we don't have to. Okay. The reason that we went back and explored properties of logs is so that we could use them. This is a quotient of logs, and you have a way to rewrite with algebra logs to eliminate quotients. And it will make it easier to do derivatives. So, with algebra, how can I change the natural log of x over x squared plus 1? Subtraction. So I have the natural log of x minus the natural log of x squared plus 1. Correct? Yeah. I still have a chain rule here. But it's not as ugly as the chain rule I started with by any stretch of the imagination. Right? Quotient rule was nobody's favorite property. It was not. It's still not going to be. So if we can eliminate having to use it on a particular problem, that's probably the way to go. Now, we haven't done any calculus yet. We haven't done the derivative. We've just used algebra, but now we can actually do the derivative of the algebra piece that we simplified. So now we're ready to do, so this is actually just f of x still. Now we're going to do f prime of x. Labels are going to be important as you're using properties of algebra alongside the properties of calculus. So what is the derivative of the natural log of x? 1 over x. And what will be the derivative of the natural log of x squared plus 1? Okay, so it will start out the same way. I think Sophia was telling me that over there. 1 over x squared plus 1. It'll start out the same way. You know, the derivative of the natural log of something is 1 over that something. And then the chain rule says I need the derivative of the something. So what's the derivative of x squared plus 1? 2x. So I'll write it here at the end for the moment. Okay, so at the point when we get to the gateway, you leave it like that, you're done. For what we're doing right now, the only thing I'm going to say that makes sense really to do is to put the 2x on top. Okay, so as a cleanup step for what we're doing, 1 over x minus 2x over x squared plus 1 is perfectly fine. You might see something where it condenses these, right, by getting a common denominator. That would certainly be one other way you might see it written. So think about, like, let's say, for instance, that you made a mistake and you're looking at what WebAssign tells you is the right answer, or you've put it into some search engine in the computer, right, some kind of a device that gives you your feedback, right? It's AI stuff, right? It may not be written like this. That doesn't mean that this is an unacceptable answer. It's just a variation that might change, and we could get a common denominator to get it to. Okay? Okay, all good? Okay. How about this one? So my guess is you're looking at that and you're saying, does it really have to be an x plus the square root? I'd rather it be a multiplication. Would be nicer if it were multiplication, right? If it were multiplication, I could use properties of logs and I could simplify it to start with. But there's no property of logs that allows me to adjust the way it's appearing when it's addition. So I don't get to use any properties of logs on this one. So just because you have them doesn't mean that they always apply, right? So this is a really good example of one where I can't use any algebra to simplify this. I really do have to use chain rules and so forth, and it's going to be messy. However, it's going to clean up nicer than you might expect as well. So we're going to start with the derivative on this one because we can't start with algebra. It's probably worth me saying it again because I alluded to it, but I don't think I really said it spot out, is if you did problem B and you used the chain rule and you didn't use any algebra, you'll get the same answer. Okay? You'll go through a different process, but you'll get the same answer and it's okay. On this one, we can't use any algebra properties, so we're going to use calculus to start with. The derivative of the natural log means I'm going to put 1 over, right? So I'm going to have 1 over. It's kind of ugly. I have x plus the square root of 4 plus x squared. And then I need the derivative of the inside. And this is the part where it's not so nice, right? So the derivative of the x is 1. What's the derivative of the square root of 4 plus x squared? It hasn't been that long. 6 weeks, right? What do you have to do? You have to do a chain rule. What do you do when you have square roots? You write it to the 1/2. So I'm going to highlight this, and we're going to kind of shift over here to the side and remind ourselves. This is 4 plus x squared to the 1/2. So you're right, we have a chain rule. What happens to the 1/2? It comes down as a constant multiplier. I rewrite the inside. and I have a new exponent. Right? This isn't a property of logs issue. This is a chain rule. I need to subtract the exponent. This is negative 1/2. And then what? Times 2. X. 2x. Yep. Okay, so if we were doing, I guess I've got one more parenthesis here. If we were doing gateway, we would stop right there, be fine. And I know you wish we could stop right here anyway. It actually cleans up really nicely, so bear with me for a couple of steps and you'll see some things collapse in a very nice fashion. You probably see something collapse right away. Do you see something right away that's going to be collapsing? The 2 here and the 1/2 part here. Those 2's are going to cancel right away because they're both multiplication factors of the part that's in parentheses, right? There's a 1/2 times 2x, so that's going to be x. So at the beginning, I'm going to rewrite this piece. I have 1 over x plus the square root of 4 plus x squared. Inside here, I have 1 plus. And then at the tail end, now I just have an x, so the x goes on top. And in the denominator, I can put it back in square root version. I have 4 plus x squared. Again, you're hoping we get to stop. We don't. I'm not going to leave it like that. That's still a mess. I do want to get all of this multiplied into a single fraction. It's not like the one before where it's just this piece plus this piece. I've got multiplication still going on and so forth. The part that's in the brackets, though, let's get that to have a single common denominator to start with, and then you'll see something lovely happen. So because it is just 1 plus that, the common denominator, of course, is simple. It is just the same denominator that's already there. So when I get that common denominator, this first piece here will have this piece as a numerator now, 4 plus x squared, plus the x that was already there. And the denominator will be 4 plus x squared square root, like this. Do you see something nice now? Yeah, I hope so. This denominator and this numerator are identical. Did we see it? So when we multiply these together, these pieces cancel. And I really end up with something that's very concise. It's 1 over the square root of 4 plus x squared. And that's it. So obviously there's other versions of how you could write this. You could write this in parentheses with the power 1/2. You could write it in parentheses with the power negative 1/2 in the numerator. In general, we want it to be written the way it began. It began with square roots, so we're going to have square roots. It began with positive powers, so we're going to have positive powers. All that kind of stuff is true. It's also probably worth reminding you that we don't rationalize variable components. So while I do have a square root in the denominator, it's not the square root of just a 3, right? It's got a variable in it. So this being rational or irrational depends on what the variable is. So we don't try to do something to rationalize it. We leave variable square roots just like they are. So I don't have to multiply by the square root or anything like that. All right, all good? All right, take a look at the next one. So if we've got absolute values involved, because we're going to need some absolute values later on for some other purposes, the derivative retains the same form. So if you have f of x as the natural log of the absolute value of x, its derivative is also 1 over x. The reason that that's the case is because if you'll remember, the interior of the log, right, the x values or the domain of the log is already positive numbers. So if there was something negative, we'd have to have it be positive, otherwise it's not defined for the log function. So for what we're working with, just recognize if you have the natural log of an absolute value, the absolute value does not affect the derivative form. And we'll do one. Here's an example. We have the natural log of the absolute value of sine of x. I'm going to look down at the note first. The note says, why does the sine of x need to be in absolute values? Yeah, the sine graph oscillates going up and down on the x-axis and y-axis. It oscillates. So some of the output values for sine are negative. But I can't have values inside of a log that are negative. We still have some zero problems because you can't have logs of zeros either. But the absolute value eliminates a good portion of the problem spots. So that's why it's there. Let's take the derivative and see how this works with a little bit of trig. What is the derivative of the natural log of sine of x? 1 over sine of x, that's where it's going to start. And I don't need absolute values, okay? So there's no absolute values in the derivative. And then I need the derivative of sine of x. Do you remember that one? Cosine of x. Again, gateway, you can leave it like that if you'd wish. But there's a nicer way to write cosine of x over sine of x. Do you remember what it is? It is cotangent of x. So this is the cotangent of x. Okay, are we good? Okay, I think we have time for one more problem, so we're going to do that before we quit for today, or at least one part of it. We'll see how far we go. Do you remember how your book likes to do this? They like to talk about derivatives, and then they like to talk about evaluating them at something, and then they like to talk about finding tangent lines. We're going to see the same thing happen periodically throughout Calc 2. So we have an equation. It's not a very exciting equation compared to the ones we've been working with. And we're going to find the derivative value because we're finding the tangent line. So if you remember, tangent lines have slope that is the derivative of the original function. So if we're asked to find a tangent line, we need to find the derivative value and find its evaluation point. So we have f of x is equal to 3x squared minus natural log of x, and we need to find the derivative of that. So what is the derivative of what we've been given? Six x minus 1 over x. You were expecting something more exciting, I know. It's very boring compared to what we're doing. This is great. This is going to give me my slope after I evaluated at the point they gave me. They gave me the point 1, 3, right? So I need to evaluate this at the x value of 1. So 6 times 1 minus 1 over 1, which gives me 5. Lovely. And then in order to put it into a line form, you have several of them. The most useful, or maybe the most directly useful, is the point slope form, which looks like that, right? Again, we did this back in November, December, and so forth. So we're looking at the slope m is what we had before. This is my 5, okay? And then the y1 and the x1 were the ones that were given to us in the problem. I think it says 1, 3 up there, right? So we have y minus 3 equals 5 times x minus 1. And then we clean it up a little bit. It's simple algebra for us. So we'll multiply our 5 through. So we have 5x. You have minus 5 and then plus the 3 from the other side, which is going to give you a minus 2. So this is our tangent line. Okay. I'm going to pause here, not just because we're at the end, but because most of you didn't bring a calculator and you're going to need it for parts B and C. So please make sure you bring your calculator next time, and you'll have that with you, okay?